Hello everyone, and in this video, we're going to be taking a look at a problem from the IMO Shortlist 2022. This shortlist only came out 3 days ago because these were problems intended for IMO 2022. So without further ado, here's the problem. Suppose we have a triangle ABC, and F is the foot of the altitude from A to BC. So AF is perpendicular to BC. And there's an arbitrary point P on F, and points D and E are defined such that PE is parallel to AB, and PD is parallel to AC. And now we construct the circumcircles of ABD and ACE. And we let x be a point on this circumcircle here, such that dA equals dx. And we let y be a point on this circumcircle here, such that EY is equal to EA. And what we wish to prove is that B, X, C, and Y are concyclic. They all lie on the same circle. That's what we wish to prove. So how can we get started on this problem? It might seem like we have to use radical axes because we have 2 points on 2 different circles, and we want to show that they're concyclic. So we might want to show that x, b, c, y, and the radical axis concur at the same point. The radical axis of these 2 red circles. So how will we show that? One way to get started is find out exactly what the radical axis is. Let's go ahead and draw this radical axis here. So here's a radical axis, and it actually seems like it's the altitude itself. So we conjecture that AF is the radical axis of the red circles. AF is the radical axis of ABD and ACE. So how can we prove this? We might let AF intersect one circle at a point P, and we might want to show that both of the quadrilaterals are cyclic. Let me go ahead and put F somewhere else so that it's easier to see. So here's F, and then here's a point, suppose M. And we want to show that ABMD and ACME are cyclic, because that would mean that M lies on both circumcircles, meaning AM is the radical axis. How can we do that? If M is the intersection of AF with one of the circles, then that means that ABMD, suppose, is cyclic. And we want to show that this implies that ACME is cyclic. Well, what does this imply? ABMD is cyclic. Because of these parallel lines, we might want to scale things down a bit. So what happens if we scale things down at, suppose, F? Then we can get EPDM is cyclic. We might conjecture that, and it definitely seems true. Here's a circle, and see how they're cyclic. So ABMD is cyclic. We want to show that this is equivalent to showing that EPDM is cyclic. And given these parallel lines, we might want to use them to our advantage. So let's try taking advantage of AB, and PE. We can say that BAM, because we're having a point M on both circles, so might as well use something related to M. So we have directed angle ABM is equal to directed angle EPM is equal to directed angle EDM, assuming that the cyclic quadrilaterals. So that's that step, and that's equal to directed angle BDM, and sorry, this should be BAM. So directed angle BAM is equal to directed angle EPM is equal to directed angle EDM, assuming this quadrilateral is cyclic. It is equal to directed angle BDM. So what we've shown is that BADM is cyclic if and only if EPDM is. And similarly, AEMC is cyclic if and only if this quadrilateral here is cyclic. So ABMD is cyclic if and only if ACME is cyclic. But M is defined as a point on AF such that ABMD is cyclic, so ACME is also cyclic. And that means that the radical axis is just AM. In other words, it's the altitude. So now let me go ahead and erase this, because we now know that it's the radical axis. AF is a radical axis of the two circles. Now we want to somehow throw the points X and Y in the picture. If we wish to show that B, X, C, and Y are concyclic, we want to prove that by the radical center lemma. Recall my video on radical axes, which talked about the radical center lemma. And whenever you extend these, if they intersect at a point, suppose, let me go ahead and, if they intersect at a point, say, P, A prime, then if they intersect on AF, then A prime B times A prime X is equal to A prime Y times A prime C. Recall this technique that I used inside the IMO video for 2008 IMO Problem 1, making it easy with radical axes. So we wish to show that XB, YC, and AF concur. Now we want to look at something special about this point A prime if we want to prove this. And we might see something off the bat. A prime is a reflection of A across F. So conjecture is that AF is equal to FA prime. A prime is a reflection of A across BC. So how can we get started on this one? It suffices to prove that XBA prime are collinear, because similar logic yields that CYA prime are collinear. So show that XBA prime are collinear. They all lie on the same line. And here's where directed angles come in. We can choose a point arbitrarily and show that PBX is equal to PBA prime, no matter what. Or some other point. It doesn't necessarily have to be P. Might as well choose a line BC because it has a lot of points on it. So we might want to show that CBA prime is equal to CBX. And now we want to use our cyclic quadrilaterals. So CBX is equal to directed angle, directed angle CBA prime is equal to directed angle ABC, because A prime is a reflection across A from A to BC, and this is equal to directed angle ABD. In other words, it's a measure of arc AD. And this is also equal to, because there are cyclic quadrilaterals, AXD. But now here's where the isosceles triangle comes in. DXA is isosceles with DX equals DA by definition. So that means that this is just equal to directed angle DAX. And then after some more cyclic quadrilaterals, we get DBX. And because D lies on BC, we get this is directed angle CBX. Hence, X lies on line BA prime. Similarly, Y lies on line A prime C. So XB and YC intersect at the point A prime, which is a reflection of A across BC. In other words, since they intersect on the altitude. Because they intersect on the radical axis, their powers must be the same with respect to each circle. So a prime b times a prime x is equal to a prime y times a prime c. And that is enough to imply that this quadrilateral here is cyclic, bxcy. So the main technique we use to solve this problem is radical axes and the radical center lemma, which states that the common radical axes, if they intersect at one point, then these points are cyclic. And we use that to our advantage, and in the end we notice that they intersect at the reflection of A across BC, which ends up killing the problem. So thank you so much for watching. I hope you enjoyed.